Yes, good evening, Yanyi. All right. Okay. Um, all right. Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh, and good afternoon, everyone.
Good afternoon, Doctor.
Good afternoon, right? This afternoon, yeah.
Afternoon, Doctor.
Is it raining on your side?
Yep.
Yeah.
Yeah.
It looks like it's gonna like get the weather is gonna get pretty bad, um, soon. Hopefully, my internet connection is not going to go bad as well with the weather. Okay. All right. Okay. Today we're gonna be looking at lecture. Oh, it's lecture 3. No, it's not lecture 3. This is lecture 2. I always have typos on my my slide. This is actually lecture 2. Okay. So I guess first of all, before we start today's lecture, let's just recap a little bit on what we have learned last week. Okay, so hopefully you still remember what is asymptotic analysis and their notation. What do you remember about them, class? What are the three asymptotic notation?
Oh, big O, big theta, big omega.
Big omega. Okay, so which one is the lower bound?
Big big O, right?
Big Omega.
Omega.
Big omega. It's omega, right? How about the average?
Uh,
Big
Big Theta.
theta, right? Okay, so do you remember like how we can compare between the two functions, and then to see whether which one is upper bounding, which one is lower bound. And then I believe we looked at on how we can actually prove them, right? Whereby we look for what is the value of n naught, and then what is the value of n, what is the value of c. Okay, then we can prove the definition of the asymptotic notation, right? And then we also look at the analysis of iterative algorithm. So you remember, whereby in order for us to um, uh, find what is the running time complexity for iterative algorithm, we calculate how many times it execute, right? So remember when we have loop, and then we try to find out how many times that the loop occurs. Okay, depending on how is the increase, how the n is being increased. Okay, so those are the things that we looked at generically. What we looked at last week. All right. So this week we're going to continue, and as I mentioned, we're going to be looking at how we can do, how we can find the running time complexity for recursive algorithm. Okay, so uh, so the way we do the analysis of recursive algorithm is a little bit different than the iterative one. Okay, so iterative is pretty straightforward. You just calculate how many times it execute. All right. So for the recursive algorithm, there are three methods that we can do. All right. One is the back substitution. Okay, we have the back substitution, and then we have the recursion tree as well as the master methods. Okay, so basically all these three are ways on how you can calculate what is the running time complexity for the recursive algorithm. So we're going to look at all these three today. Hopefully we can finish all three methods by today. All right, in this lecture. All right, so let's just look first at what does it mean by recursive algorithm. Okay, so I think in general, since you have you know how to do programming, you know you have done this before. You know whenever you have a function calls, and you have a function that calls itself, that is a recursive program, right? So a recursive algorithm, you can say that it is having an equation or inequality that describe a function in terms of of it in a smaller size of input. Okay, so in a sense you can say that the equation is something like a sub equation of the biggest the big problem. Okay. uh oh, all right, 1 second, I got distracted by message. So okay, so basically you can say that a recursive function, okay, or a recursive problem is that, let's say you have like one big problem. So let's say you have a one problem, all right, and then this problem you try to break it into smaller size. Okay, so you break it into maybe smaller problem one, smaller problem two, smaller problem three, and so on and so forth. So up until smaller problem k, let's say for example. Okay, and then each of these will have a sub solution. So each of these will contribute into solution one, sub solution two, sub solution three, and up to sub solution k, and then finally you will merge it back to get the whole solution. Okay, so basically this is what does it mean by having a recursive problem. All right, so bear in mind that so if you see here, I mentioned here, so whenever you talk about recurrence, it is always hand in hand with the divide and conquer paradigm. So divide and conquer is an algorithm design paradigm that you apply if you have a problem that you can break it into smaller sub problem. Okay, so basically the divide and conquer paradigm gives you a natural way to characterize the running time complexity by dividing and conquering the sub problem and then merge it back. All right, so bear in mind so basically this and also you have to bear in mind when you talk about breaking down the problem into smaller sub problem, each of the sub problem is the same. Okay, so let's say for example you cannot say break, so in a sense when you break the sub problem, each of the sub problem is the same sub problem. You cannot have a different sub problem. Okay, so, and then after that you need to merge it back. So that is what it means by recursive algorithm. Okay, so for the properties of the recursive function, there are two ways that you can there are two things that you need to consider, okay, when you want to analyze the running time complexity for recursive function. One is you need to you need to find out or assume what is the base case. Okay, so the base case is where you need to know what are the terminating scenario for that recursion, whereby normally when you have this terminating scenario, it is when the recursive will stop produce answer. Okay, so you need to determine what is the best case, and then after that you need to also look at what are the set of condition, how you can reduce basically the problem towards the base case. Okay, so you have the biggest sub problem, and then you need to find what are the condition on how you can break it down and at the same time, like moving towards the base case. So we're going to see later on what does it mean by this. Okay. So all right. Okay. So let's try and do this for a while. Try to transform this iterative program into recursive program. So as you all know, any iterative program you can transform it into recursive program and vice versa. Okay, it's just that when it is in iterative form, uh, the analysis is different. If you compare it with the recursive program. Okay, so basically you may have two programs that does the same thing, but one is iterative, one is recursive. You can analyze both, but the way you analyze both is different. The way you analyze iterative program is how you would do how we do it last week, and for the recursive program, you can actually use the three method that we're going to look today. Okay, so can we try and do this for a while and see whether you can uh, translate this into recursive program class? I gave you like 2 minutes. And then can you please share it on in the chat if it is possible? So how would you do it? So this is function 0. And then you have some parameters. How should you do it? If I is the n bigger than 0, print hello world, and then we return n minus, sorry, function 0 n minus 1 plus, is this correct? Is this correct? Are you all there? You're so quiet today.
Maybe you can start with the base case. So like I'm thinking if possible, like maybe if n equals 0, then return. If n equals 1, right? Then you return the hello world. You print hello world.
Can you write your answer in the chat? I didn't know. Can you give me 1 second? Oh, where did my slide go? Oh, my slide went somewhere else. Okay. Anybody share answer already? Function if n is equals to 1, print hello world as print hello world and function n if n equals to 1, print hello. Anybody else got a different answer? This one, print hello function and minus 1 else return. Yep. Return hello world, print hello function 0 and minus 1. Right? Okay. Yeah. So the base case, in a sense, in this case, it looks like everybody have a different way of writing the base case, but none of them is, all of them are acceptable, are accepted. Okay. So later on, when we want to do the analysis of this recursive function, this is the base case that we need to bear in mind. Okay, we need to make an assumption there. All right. Okay, good. Thank you. All right. So basically, this is another example. This is actually another example, okay, of a recursive function. All right. So this recursive function, as you can see, it's almost the same that like what we have previously. It's just that our n is more than 1, right? And you can see that over here, we have a function that calls itself with the value that of n minus 1. All right. All right. So as I mentioned just now, there are 3 methods for solving the running time complexity or solving the recurrences, and they are the substitution methods. Okay, where we try to guess, doing an induction to prove, to use some mathematical induction to prove that our guess is correct. Okay. And then there are the recursion tree method. Okay, so basically we're going to draw a tree and then see how does the recursive tree goes down to the base case. All right, and finally the master methods, which is actually actually it is the easiest way to actually calculate the recurrences of the running time complexity of a recurrent of recursive algorithm is to use the master method. But you need to understand how to use the substitution method and the recursion tree method. Okay, so so master method is actually you have a formula already. All you have to do is find some values and then you plug it in and then you straight away can get what is the running time complexity of that recursive algorithm. But you still need to know the substitution method, the recursive tree method, so that at least you know how the running time complexity is that you get the running time complexity for the recursive function. Okay, so this is another example of a recursive algorithm, the factorial. You know, right, what does it mean by factorial? So a factorial is a function that calculates the product of all positive integer less than or equals to n. Okay, so like let's say you have in order for you to calculate what is 5 factorial, so 5 times there's another 5 typo 5 times 4 times 3 times 2 times 1, right? And if you are to implement a factorial program, basically this will be your pseudocode, right? Where you need to check that n is not is less or equals, if n is less than equals to 1, you need to return 1, else you need to recursively call the same function with n minus 1. Okay. All right. So basically, the running time of a recursive algorithm can be expressed using this recurrence relation. Okay. So how do you actually came up with this? So as you can see, so let's look back at this program. All right. So let's try to see where are we are still calculating. It's just that we do not know how deep is the recursion tree is going to go. So that's why we so in a sense we are still counting. It's just that the way we count, we try to make a guess or you know, like using substitution method, recursive tree. Recursive tree, you can actually see how far the tree goes down. And for the master method, there's actually a magic formula that you can plug in, and then you can get the running time complexity. But for now, in order for us to see how we can come up with the recurrence relation, let's try to trace this one. So basically, we want to know how many times. So we want to know what is the running time complexity for this function, right? And we know this one will take order of 1. And then maybe we have another one here, right? But this one, we have no idea, right? So basically, in this case, the running time complexity for this one would be Tn minus 1, right? So from here, we can actually write the recurrence relation, okay? Whereby the recurrence relation for this factorial function would be, we have this equals to Tn minus 1, all right, plus all the constant, okay? So maybe again, since we do not like really care about what is the constant value, we can always like generalize this into 1, or maybe we can put like a C or a K. So basically the constant, we can assume it to be 1, okay? And therefore we get the recurrence relation. So what is the base case in this case? What is the base case? So when t is equals to 1, n would be, when will it stop calling the recursive, calling the factorial function?
It will stop at return 1.
It will stop when n is equals to 1, right? Okay, so basically our base case is T1 when n is equals to 1. All right, so that would be our base case. So yeah, so if we look here, so basically that is how we get our recurrence relation. Okay, so we have the recursive call on n minus 1 time. Okay, and then we have 1 for all for other constants operation, and then we manage to we identify what are the best case where the recursive function where the recurrence will stop. Okay, all right. So that is how you do the recurrence relation. Okay, so let me see the previous one. Is it the same? Yeah, I guess this one is also the same. N is bigger than 1, so the base case is 1 as well, right? For that one, what is the base case for this one? This function? Plus
1.
base case is 1, right? Okay. All right. So that is how you write the recurrence relation. Okay. Okay. So you can also write it this way. All right. So since we have this, so we can also write it for the recurrence relation of T of n is equals to, so T n minus 1 plus 1 is when n is more than 1, and when n is equals to 1, is the stopping value would be 1. Okay, the running time complexity for when n is 1 would be 1. Okay, you cannot have time 0 because 0 is also a constant. So normally we will take 1, or as I mentioned just now, 1 or c or k. So you can also you can put any value of constant. So normally we don't use 0, we will put 1. Okay, if it is constant. All right, so you can also write it this way, the recurrence relation. All right, so let's look at, oh, sorry. I pressed my, okay. So, am I still sharing? No, I'm not. I accidentally pressed the power button. Okay. All right. So let's look at the first method, which is the back substitution method. Okay. So basically, when we do this, okay. Dr. Raja is here. Okay. So before we start, maybe I would like to invite Dr. Raja to, she has some announcement for you in regards to the tutorial group. Okay, Dr. Raja?
Okay, so
yeah.
And hi everyone, my name is Dr. Raja Jamila binti Raja Yusof. I'm teaching the one of the tutorial class for this course algorithm. So my announcement is that if you want to be in my tutorial class, you have to re-register to be in my tutorial group. And if you are from my tutorial class and you want to go to another lecturer's tutorial class, which I do not encourage because the other lecturers have already a lot of people to deal with, so you need to do the same thing. So please do it as soon as possible because I think you don't have much time to do that. I think only this week that you can do that, but after this week you cannot do that again because why we want to stress that you register in your own you go to your own tutorial class is that because of the C-test. One is the main thing is the C-test because you will be evaluating the lecturer that you are registered with. Even though you go to another lecturer's class, then if you register, you do the C-test, it will be for the lecturer you are registered in. So you want to have that to be as accurate as possible. And just to tell you that my class has got only around 25 students. The total of the two tutorial groups, two tutorial groups, 25 students in total. So I'm not sure whether you are keen to have a lot to be interacting with me in my tutorial class, but I would encourage you to join my class so that we can have a better interaction between each other. And just to brief you my past experience, I've been teaching algorithm for the past 5 years, even before Dr. Asmiza was teaching the course, and I'm also teaching advanced algorithm in the Master of Computer Science. Just in case if you guys have doubts whether I can teach you algorithm or not. Okay, so just to repeat myself, if you want to be in other lecturers' tutorial group, you need to register in their tutorial group. And if some other students from other group would want to come to my tutorial group, you have to do the same thing as well. And you need to do it as soon as possible. Okay, so that's it. Thank you and have a nice day. Okay, Dr. Smiza, you can continue. Okay, bye-bye.
Thank you, Dr. Raja.
Yeah.
Okay, so for those of you who would like to change the tutorial group, because I think this week will be the last week, I guess, for your add and drop. So yeah, so you can always change your tutorial group. As you heard, Dr. Raja, she was teaching longer than me. So yeah, so don't worry about what she can actually usually she's teaching the class, I guess. Yeah. Okay, where were we? Oh yeah, so we were doing the substitution method. All right. So okay. So let's look at the first one. Okay, the back substitution method. Whereby in this substitution method, what we're trying to do is that we're trying to guess. Okay, what are the solution? We don't really like, because the induction, there are some values that we assume. So we try. So in a sense, when we do this substitution method, is we trying to guess what are the solution, and we're going to use the mathematical induction to find the constants and how and show how it is going to reach that base case. Okay. So since we're doing mathematical induction, so you have to actually some of the mathematical formula that you're going to be using is included in the mathematical preliminary. So if you remember last week, I did mention about you going through that mathematical preliminary, because we are going to use this when we do the back substitution method. Okay. So let's try and do this for this question. Okay, so where is it? Where are we? Okay, so maybe I'll just add one page after, and I think you don't like black, so let's use white. Okay. All right. So let's try and do back substitution method. I always cannot see some very difficult words. Okay, back substitution method for this recurrence relation. Okay, so we have t of n equals to t n minus 1 plus 1. All right, so now we're going to do back substitution. Okay. All right. So the first step that we're going to do is that we're going to call this as equation 1. Okay. So we know that for the next recurrence that will occur is calling this function, right? The next function call would be this one. So we're just going to try to write an equation in terms of when t is equals to n minus 1. Okay, so when t n minus 1, we're going to get n minus 1 plus 1. And what are we going to get here? T n minus 2 plus 1. All right. Are you following so far? Any questions so far? So we're going to call this as equation number 2. Are you good so far, class?
Yes.
Yes.
Yes, sir.
Yeah.
Yeah,
Okay. So let's try and do it one more time. Okay. So as you can see here, the next call would be when t n minus 2, right? So we're going to do another one whereby when t is n minus 2, we're going to get t n minus 2 minus 1, right? Plus 1. And what are we going to get? T n minus 3 plus 1. So we're going to call that the equation number 3. All right. So we have all these 3 equations already. So we can use it to substitute it back into the equation. Okay. So let's try to substitute. So for equation number 4, for the next step, we are going to substitute 2 into 1. Equation 2 into equation 1. Since in equation 1, we have Tn minus 1, and we have found what is t minus 1, which is t minus 2 plus 1. So we're going to substitute that into the equation. Okay. So we're going to get t of n is equals to t. What is tn minus 1? So we have tn minus 2 plus 1 plus 1, right? Correct? Right? Which we're going to get tn minus 2 plus 2. Alright? So that would be equation number 4. We call this equation number 4. Alright, so now in equation number 4, we have this tn minus 2. And we already know the tn minus 2 is equals to this. We're going to put it inside there. We're going to substitute tn minus 2 inside equation 4. So we're going to put equation 3 into equation number 4, right? So what are we going to get? So we're going to get tn minus 3 plus 1, right? Plus 2. So are we going to get finally tn minus 3 plus 3, right? So that is what we're going to get. So from here, you can already see a pattern. Do you see a pattern? So right now, as you can see, this thing is going to go down some k times, right? It's going to occur 4k times. This thing is going to like go like down. You're going to keep substituting until 4k times. So what do you think happened when you reach that k? What is the pattern? We can say that it would be
tn minus k plus
n
k
minus k plus
plus k.
k, right? Okay, so when we know that so now we know that basically the last the recursion will stop when it reaches tn minus k plus k. All right. So how do we go after this? Okay, after this step, we know what is the base case, right? So what is the base case? T1
1
is equals to
1
1, right? So therefore, we know that this is equals to 1, right? So we can find what is the value of k. So we can say that n minus k is equals to 1 and k is equals to n minus 1, right? So now we find our value of k. We can substitute the value of k inside this equation. So we can say that our t n minus 1 plus n minus 1, right? What are we going to get? N minus n plus 1, so we get 1 plus n minus 1, right? Which is,
n.
we're going to get n. So the running time complexity for this recursive function would be order of n, or you can say theta or big omega or so on and so forth. Okay, so basically the running time complexity for this recursive function tn minus 1 plus 1 would be order of n. Okay, so are you good so far for this question? Any question? Anything you don't understand? Class?
The base case, we
Mm-hmm.
got it because from the last equation, the formula would stop when n is equal to 1, right?
Yeah. No, T1. Well, when T1, this one, when, because T time cannot be zero. Oh, sorry. Because T cannot be 0. So we always say that T is equals to when T1, and then the base case is when n is equals to 1. Some base case we have n is equals to 0, but since we have this is actually for factorial, right? If I'm not mistaken, this is a recursive relation for factorial. So the base case is 1. All right. So therefore, we can see that the running time complexity for this recursive function is order of n, right? So this is the same, but I just do it like manually just now, all right? So we already know that that is 1 just now, T1. So this one is actually T1 because this is 1. So therefore, this is actually, this is actually T1, right? Okay. So that is the substitution method. So let's try and do another one. So it's a little bit different because we have instead of constant we have another
Doctor, you are muted.
Doctor, you are muted.
how long have I been muted?
Just for a second.
Just
Just now only.
okay. I don't know how it got muted now. But anyway, all right. Let's try and do this substitution method on this question. You want to try first? You want to try first? I give you like 2 minutes. Maybe if you can get the three, or you want to go through with me first. We have the same. We have several question in our tutorial as well. Maybe we do this together for now. So I think do we have time? Oh, it's already 3:43. Oh my God, we still have two more methods to cover. Okay, maybe we'll just do this together. Okay. So we have the recursive function. We have t of n, tn. What is it? Tn minus 1 plus n. What is the base case? When t is 1, n is equals to 1. Okay, so let's try and do the back substitution method. All right, so we can say that this is equation 1. All right, so we're going to do for t n minus 1 is equals. Sorry?
The base case here is the same for the one in the factorial equation.
Doctor, you got muted.
Why am I muted? I'm not pressing anything and somehow my mic is suddenly mute. Okay, please let me know if I'm muted again. Did I have? No, it's not on my keyboard or anything. My keyboard is clear. But anyway, in this case, because since we do not have the how do you call it? Maybe the program for us to determine what is the base case. Okay, so normally this kind of question they will provide you with the base case. Okay, so in this case we assume that the base case is when t is 1, it will be n is equals to 1. Is that all right?
Yeah.
Okay. All right. So let's try and do this. Okay. So we have this equation. Okay. So now we're gonna do for t n minus 1. So we get so basically if we put it in, so you're gonna get t n minus 1 plus n minus 1. So are you going to get t n minus 2 plus n minus 1. So we're going to call this equation number 2. Right? So let's do another one whereby t is n minus 2. We're going to put it in equation 1. So we're going to get t n minus 2 minus 1 plus n minus 2. What are we going to get? T n minus 3 plus n minus 2. Okay, so this is going to be our equation 3. Are you good so far?
Why didn't we continue in equation 2 and make it t to n minus 3?
Because you can actually. It's just that the reason why we have like only like until equation like t n minus 2 is because normally by t n minus 2 we already can able to see the pattern. You can actually go on until you get what, but then you need to know, because we are trying to make a guess, so we need to see what are the patterns. How does the recursion completes, break down and then produce the final solution. Okay, so in this sense, we only do it up until n minus 2, is because normally by then we can actually see what are the patterns for that relation. Okay, so in this case, let's continue. So we're going to put 2 into 1. Okay, so since 1 we have the t n minus 1, and we know that t n minus 1 is this equation. So let's put 2 into 1. Okay, so what are we going to get? We're going to get t of n is equals to t n minus 2 plus n minus 1 plus n. Right? Right? In fact, we already see a pattern here. Do you see the pattern? So let's try to put in, so let's say this is equation 4. Okay, so let's put in 3 into 4. What are we going to get? We're going to get t n minus 3 plus n minus 2 plus n minus 1 plus n. Do you see the pattern already? See the pattern? Right?
Yeah.
So now, again, this is going to happen for k times. So how are you going to write the k equation now? Thus, how are you going to write it? So we have this is n plus n minus 1 plus n minus 2 plus n minus 3 up until
N minus
what? N?
minus k.
Minus k.
N minus k plus t n minus, what happened? Because if this one, what are we going to get? n minus k plus 1, right? So we're going to have n minus k plus 1, right? That's right. Okay. So we know that this is the final, how do you call that? Final recursive call. And we know that for a fact that the base case is equals to 1, right? So can we get the value of k now? So what is the value of k? What is the value of k? So we know that n minus k plus 1 is equals to 1, right? Because you know that t1 is equals to 1, right? The base case. So what is our k now? What is our k? What is our k? K would be n minus 2. All right. So we're going to plug in our k n minus 2 inside our equation. So n plus n minus 1 plus n minus 2 plus n minus 3 plus, I'm so sorry, my handwriting is so crazy. So our k is n minus 2. So we have, maybe I will just erase this one a little bit so that it won't be so messy. Oh, sorry. So we have k plus 1 here, right? So if we plug in our k value, we have, n minus 2 plus t n minus 2 plus 1. Okay, so we know that this with the basically this will become, so you write it back, will become n, so you become what? You will become n minus n plus 2, so you become 2. I think I better write it so that you won't get so that we can see the what. So we get n plus n minus 1 plus n minus 2 plus n minus 3 plus, and then this one we will get 2 plus this one would be 1. Oh, sorry, would be 1, right? So what is this? What series is this? Class?
Arithmetic.
It's an arithmetic. Yeah, arithmetic series, right? So we know that the arithmetic series would be, what is the formula for arithmetic series? N plus 1 over 2, right? And therefore, we can say that the running time complexity for the recursion will be order of n squared. We take the higher order term, remember? So we know that the running time complexity for this recursive function is order of n squared. Okay, are you all good? You all good so far? Any question about this? Any question about this? Okay. So need to do practice. Yes. For the tutorial, I think we have a few questions inside there. I don't remember what is the tutorial question, but try and do that one. And see whether you can do it or not. Okay. So yeah. And you can always get like additional question. I don't know whether I have any extra questions inside my slides, but maybe you can find it. Okay. But you have to do the practice. But basically the concept, do you see anything that you don't understand? I mean, like from where it came from and so on and so forth, in regards to the mathematical induction. Okay, so I take that as a no. Right?
So I
Yes.
have one question.
Okay.
Just a quick explanation on how we get the value of k. I don't quite get that. Sorry.
The value of k. You mean how do we get this last term? Is it?
Yeah, exactly.
Okay. So how do we get this last part? Okay. So if that's why I said just now, I think when your friend asked why do we need to do only until n-2, because you want to discover the pattern. Okay, so as you can see here, this we have a pattern here. So we have n-1, n-2, n-3, and basically, in order for it to complete counting or trying to find a solution to the recurrence, this we can guess that this would be the last term. Okay, whereby we have n minus some k, because it's 1, 2, 3, and it would go up until some k value. So that's why we say that this will be going up until n minus k plus the last the T1, which is, we know that from the pattern. So when you have t n-3, it will be plus n-2. So that's why we get the n minus k plus 1. So that is how you get the k. That is how you get the last term. Same goes for the previous question just now. Okay, where we have the pattern, and we know that this is going to run up until some k value, some k times. And since we know that how it grows is that first is n-1 plus 1, and then it become n-2 plus this is actually plus 2. n-2 plus 2. Okay, and then the other one is n-3 plus 3. Oh, sorry. Yeah. So this is n-1 plus n-1 plus 1. And then when we put in, we get n-2 plus 2. And then we get n-3 plus 3. And we know if we go down, we're going to reach into some k times, where we're going to get n minus k plus k. Okay? So that is how you get the k. Is that all right? Is that all right?
Okay.
Okay.
Yeah, thank you.
All right. Okay. So that is for back substitution method. Okay, so we have looked into two example. Maybe you can try in our tutorial, and then see whether you can actually get this. I think we have a typo here. I don't remember where is the typo. There's another typo around here. Never mind. I think I marked it. Okay. All right. So, okay. So, do you want to take a break for a while, like 5 minutes before we go into the recursion tree method? Or you want to continue? Class? Let's take a break for a while, right? Okay, so we break for 5 minutes. I will come back at 4:05. Okay, since I need to go take a break as well for a while. I need to go to the washroom. Yes.
Can you stop at the slide where the example 2?
Sorry?
Stop the slide. Up.
You want to see the workings?
Yes.
Okay. There you go. All right. It's the same like the one in the slide. It's just that because since I do it manually, I like to so it's just the same. It's just that sometimes I flip it, just so that it will help my explanation. It's the same like the slide. Okay. All right. So I'll see you 4:05. slide 18 should be n minus k plus 1. I'm not sure which one you're referring to. Step 7. Step 5, step 6, step 7. Oh yeah. Okay, wait. So, you mean this one. So is it the same answer? Should we get the same answer? So it's just the bracket. Okay, thank you. All right, so okay, one tanya. So K is always the second last in the sequence. In a sense, it is not. It will be the last and the second last. Normally, how it's not the second last. Should we say it's the second last? Because K would be where you reach the base case. K is where the value is where you reach the base case. Okay. So for example, the first example. Yeah, it is where the K plus 1 is passed. Yeah, because when K plus 1, when it passes the base case, it stops. That's why we put K plus 1, because when K plus 1, the value of T, the value where the base case is stopped already exceeds. So the recursion stops. Yeah. Okay. All right. Okay. So can we continue? So let's look at the second method, which is the recursion tree method. This is also something that you use to guess, okay, what is the running time complexity for a recursive algorithm. Okay, like for me, this is my least favorite method because I don't like to draw the tree, but we have to go through this. Okay, so basically, in this method, you literally have to draw the tree. Okay, whereby each of the node will represent the cost of a single subproblem. Okay, for each of the recursive function invocation. So basically, from the tree, we are going to determine what is the total cost. All right. So basically, when we draw the tree, we should be able to calculate what is the total cost, and then we're going to sum the cost within each level of the tree to obtain at each level how many normally I call it like how many work that is being done for each of the level, and then we're going to sum at each level how many work has been done. Okay. So as I mentioned, you use this method to have a good guess, okay, on the running time complexity, and you can always verify it either by using the substitution method or using the master method, okay. But I think once you know how to use the master method, you're not going to do any of these two method already. Okay, but it is good because you need to know how does the recursive algorithm is the running time complexity for recursive function or recursive algorithm is being calculated. All right. So let's look at the first question. Okay, so like let's say we have this function. We have function 2. Okay. We take in some parameters and we need to check if n is equals to 1. We're going to stop. Okay, so basically we can say that our base case. So our T1 is also equals to 1, right? And then else, you are going to do this. You are going to call function 2 to, for 2 times. You're going to break it into 2. Okay? So here we can write our function recursive function relation. So we know that for the if statement and the return, we can always say that this costs S1, or we can say that it is some constant value C. And then in this case, we have how do we break it? We have 1 T n over 2 as well as T n over 2 over here. Okay, so we have two recursive function here. Okay, it's called by these two functions. So therefore, we can write the recursive function relation as, so since we have 2, so we can say that Tn is equals to 2 T n over 2 plus C. Okay, or you can put it as 1 or C. So it doesn't matter. C means it's a constant value. Okay. All right. So we have our base case. We have our recurrence relations, recursive function relation. And let's try to draw the tree. Okay. Okay. So basically we can write it this way as well. So we know that for Tn, when Tn over 2 plus C, n is more than 1. And when n is 1, it will stop. This would be our base case. So this can also be equals to 1 or any constant value. It can be k, it can be a, and so on and so forth. It's just a constant value. Okay? All right. So let's try and do our tree. Okay? Let's try to do our tree. Let's let me add some page here. Where are we? Over here. Okay. All right. So what is our recurrence relation? So we have Tn equals to 2 Tn over 2 plus C. Okay, so what happened here is that, okay, so maybe I'll trace it one by one. So basically what happened here if we trace our recursive relation, what happened is that for the first level, we are going to produce this work, and then after that we're going to call T n over 2 and T n over 2. Do you see what happened here? So at the first time, the recursive call, we are going for the first recursive call, we are going to generate this amount of work, okay, and we are going to call 2 Tn minus 2. All right. All right, and then what happened in the next recursive call? So basically, at this level, okay, at this level now, this will produce C, right? And it will call, since now our T is n over 2, this one become T n over 4. This one is going to become T n over 4. And this one also will produce the work C, and it will go down to T n over 4 and T n over 4. Are you following so far? Class?
Yes. What do you mean by producing the work C?
Because this one is completed. So meaning that for this constant, it has been completed. It has been completed. So this is the so basically this operation is being done at this level.
Oh, okay. All
Yeah.
right. Got it.
So later on we're going to see an example where this one is not a constant, and then we will see much more clearer what are the things that happen at that level. Okay. All right. So, but then, do you know how do you get like from n over 2 into n over 4 over here? Do you see what happened? Remember when we do the back substitution method, where we sort of like n minus 1 and then n minus 2, n minus 3. Same goes for this one. So for the first call, it would be Tn, n over 2. And then this one, it become, when we call the function again, so this is already done. So these are the work done on that level. We're going to call function Tn over 4, right? So again, we can continue going down just to see, just again, because we need to find the pattern. So this one, we're going to produce C, this one is going to produce C, we're going to produce C here, going to produce C here. And what will here be? N over
8. Tn over 8.
N over 8. Yep, that's right. Good. N over 8. T. N over 8. T. N over 8. Oh my God, this is the reason why I don't like to draw the recursive tree. Normally towards the end, my tree becomes the haunted tree or something like that. Okay, so same goes for this one, N over 8 and T N over 8. Okay, so I think it's enough because we kind of like already see a pattern here. And do you know how so from here we know that this tree is going to go down until the base case. Okay, so what is our base case right now? In this case, basically this is going to run down until T is T1.
T, yeah.
Right? So we know that it's going to run until T1. All right. So now we are going to calculate at each of the level. All right. So basically this will be like, so this one will be, so T1, everything will be T1 and so on and so forth. So now we're going to calculate at each level, at each of these level, how many work that has been done. Okay. So in this case, this would be C. This one would be C plus C would be 2C. This one would be
4C.
4C. This one would be 8C. Right? So we can also how do you call that? Say that this is 2 to the power of 1. So this one is 2 to the power of 2C. This one becomes 2 to the power of 2 to the power of 3C. And basically, you know that as it approach the base case, we are going to do 2 to the power of
K.
2 to the power of K C.
C.
Right? So that is our tree. Now we are going to calculate the total cost of all this work that has been done. All this. Okay. So what are we going to are we going to get? So our Tn is going to be 2 to the power of 0 C plus 2 to the power of 1 C plus 2 to the power of 2 C plus 2 to the power of 3 C plus up until 2 to the power of K C. Okay. And then we can factor out the C. We're going to get 2 to the power of 0 plus 2 to the power of 1 plus 2 to the power of 2 plus 2 to the power of 3 plus 2 to the power of K. Are you following so far? Yeah?
Yes.
Yep.
So what is this? This is another series. What series is this? It is geometric series. Okay, so geometric series, I don't remember what is the geometric series. What is the formula for geometric series? So you're gonna get like C, I'm just gonna look here. I don't remember the formula, but it's in preliminary, what? So we have, we have 2 to the power of K plus 1 minus 1 over 2 minus 1, right? Please check the GP series, geometric series. I don't remember the formula. Okay, so basically if you apply the geometric series, you're going to get this. Okay, so what can we say about how can we find the value of K here? Class? How do you find out the value of K? We know that 2 to the power of Kc or 2 to the power of K is equals to what?
1.
Is equals to 1? 2 to the power of K. So I don't think so. 2 to the power of K. Okay. So right now we have to make an assumption. Okay, because we know that for remember when we have the base case, remember the last question where we have some n minus k. So we know that at this point we need to assume that in order for us to reach this k, we're gonna have like, we can say that n minus k should equals to 1, right? So here we're going to make an assumption. When n is reaching k, this will become 1. So we can say that our k value is n minus 1 over here. Okay. So we can put in our c value. So our c here is 2 to the power of k plus 1 minus 1. So if we put in our k n minus 1, okay, k n minus 1, so we're going to get c 2 to the power of n minus 1 plus 1 minus 1. We're going to get, order of 2 to the power of n, where we ignore all the constants. Is that right? So over here, because we need to make an assumption of our base case, because this our value, in order for us to get into the how do you call that, the stopping the base case, we can make an assumption that when n minus k is equals to 1, therefore we can find our k value which is n minus 1. Okay, you get what I mean, class?
Yeah.
Okay. All right. Any question about this one? Any question about this one? You good? Maybe later on when can you repeat the assumption part? Okay, so for the n minus k, all right, so we know that in order for this recursion tree to stop, n has to be basically it has to be like just now when we look at the previous example where the stopping value has to be 1. So when the n is equals to 0, it will stop. Okay, so basically we can say that the assumption when basically we need to make sure that when n is n minus k, it has to equals to 1. So at least we know that before it stops, how do you call that? For meaning the last and the for the stopping base, and then we want to know what is the value before we know the value before the stopping would be 1. That would be the stopping case. That's why we make an assumption that n minus k must be equals to 1. Do you get what I mean? Class? Right? Okay, so that is for example number 1. Let's try and do example number 2. We're trying to make a guess. We try to find like, like if you remember when we do our iterative function, we try to like anticipate how is our function is going to reach the last term. So in a sense, yes, when we say the n minus k before it reaches 1, I think it's not before it reaches 1, it already reaches 1. Yeah, I guess it would be you're trying to find, so if you say n minus k, yeah, I guess you can say that before it reaches the base case. That's why you make an assumption that n minus k is equals to 1. Okay? All right. Okay. All right. So let's do the second example. We have we have half an hour. We have another method to go. But I think for the master method, it will be very fast. Okay, so let's look at the second example. Okay, we have Tn to Tn over 2. And this time, our n is, it's not constant, but it is another. So we can say that our T1 is equals to 1. Okay, so same thing. Okay, we're going to look at, we need to calculate the work level by level, right? So in this case, for the first level, so the first level, what happened is that we have n completed, and we have t n over 2 and t n over 2. Okay, so at level at the first level, so normally we call it, this is level 0, this is level 1, level 2, and so on and so forth. Okay, so at level 1, what happened? What is what is the work completed here? It would be, so this one, since it's n, so the work completed would be n over 2. This one is also n over 2. And then you will call another 2 t n over 4. T n over 4, t, n over 4, and t, n over 4. Alright? So now what happened at level 2? Level 2 going to level 3. What happened? What is the done here? And
N over 4.
n over 4, n over 4, n over 4, n over 4. And this will go down to t, n over 8. Okay? And so on and so forth. T, n over 8, and so on and so forth. And it will go down until t is 1. Right? Okay, so now we are going to calculate at each level how many work that has been completed. Okay, so in this case, this level, how many? It would be n. How about this level? It would be n plus n over 2 plus n over 2. It would be n.
N.
Right? Same goes for here. So n over 4 plus n over 4 plus n over 4 plus n over 4. We're going to get n. So we can say that at each of the level would be n. Oh, sorry. Be n. Until we reach down here, this will also be n. Right? Okay. So now, how are we going to calculate the running time complexity for this one? So we can say that Tn is equals to n plus n plus n plus n plus n plus n for k times. Right? So what is k in this case? What is k in this case? Plus, what is our k in this case? It would be the level, right? The level of the tree. So what is the height of the tree in this case? How do we find the height of the tree? What can we get from here? T1, we can also say that this is this level is also T n over 2 to the power of k, because this one we can say that this is n over 2 to the power of 1, this is n to the 2 to the power of 2, this is n to the power of 3, and basically at this level we can also say that this is n t n to the power of k. So basically this is equals to 1. So what is our height, which is k? It will be log n base 2, right? Anybody like got lost? This one, T1, we can also say that it at level T n over 2 to the power of k. And since we know that this is 1, we can find what is the value of k. So therefore, we can say that in order n times the heights, right? Which is log n base 2. So this is the running time complexity. for this would be n log n. Class? Okay? So that is how we sort of like make a guess. When we draw the tree, we can see how it being divided until it reaches the base case. Okay, until it approaches the base case. So are you okay in this sense? Class? Yeah. Any question about this one? Any question about this one?
Doctor,
Mm-hmm.
it can also become log n power n, right?
Sorry? Log n?
Log n power n.
Log n power n.
ఎన్న ముందరకు వచ్చింది శ్రీజ.
Yes, I think you can. Yeah. N power of n. Okay, n log n. All right. So that is for the second example. All right. Okay, so we have like another 20 minutes more or less on how we can look at the final method, but this is actually very simple. You will see that why like once you know this thing, you will like ask why do you need to know the back substitution and the recursive method. Okay, so for the master method, it actually gives you a sort of like the equation or the formula where you can just plug in the value and then you can get the answer. Okay, so for the master method, normally our recursive function, okay, will look like this. Okay, we'll have this form. You're gonna have some function here, recursive call, and another function over here. So normally, excuse me. So normally this one we can say that this would be our g of n, and this one will be another function which is f n. Okay, and we need to make sure that our a is more than 1. Okay, our b a is more than equals to 1 because you can also have like 1t. B is more than 1, and for fn it has to be asymptotically positive function. Okay, all right, so this is the condition for applying master method. All right, so let's let's look at this. This is the condition for master method. Okay, so the main pattern of recurrence, you need to be able to identify this. Okay, so this is A, this is our B, this is our K, and this is our P. Okay, and we also need to know what is our Fn, whereby as we see just now, A must be more than equals to 1, B must be more than 1, our K must be, because it has to be asymptotically positive, so K has to be more than equals to 0, and our P must be a real number. Okay, so our log n power log power P n. Okay, all right, so based on this pattern, okay, we are going to use this. There are 3 cases for a master method. Okay, so for case 1, so basically after we identify what is our A, what is our B, what is our A, what is our B, what is our K, what is our P, we need to find out what is log A base B. Okay, we need to find out what is the value for log A base B, and then we are going to compare it with the value of K. Okay, so if you look at this condition, this is the condition that you need to compare. We find what is log A base B, and then we compare it with K. And then if log A base B is bigger than K, the value of this is bigger than the value of this, okay, then you can straight away just write the Tn, the running time complexity for that function. Okay, that is for case 1. So case 1, if log A is bigger than K. For case 2, there are 3 conditions. Okay, again you compare log A base B with K. So for case 2, these 2 values is the same, but you need to look at the value of P. Okay, if P is more than -1, then this would be the answer. You just plug in what is the value of K, the value of P, and that will be the answer. Okay, and then if P is equals to -1, then this will be the answer. If P is less than -1, then this will be the answer. Just plug in the value. Okay, and for case 3, when log A base B is smaller than K, then we need to check what is the P value. If this is if the P value is this, meaning the P value is bigger or equals to than 0, then this will be the answer. You just plug in what is the K, what is the P, and that will be the answer. Okay, same goes for the last one. If P is less than 0, and then this will be the answer. You just straight away order of n to the power of K. Okay, so let's try and do this exercise. This is some example. Okay, so we have this. Okay, so it's already mentioned here. This is an example of case 1. Okay, so we need to find what is A. So A is 16. B.
4.
B is 4. What is our Fn?
N.
What is our K? What is our K? So this one we can also say that it's order of n to the power of n to the power of 1. 0. Or is it 1? K is 1.
Yeah.
And then log 0 n is the same as this one. So what is our K? K is 1. P is equals to
0.
0. Okay, so now we'll just plug in into our formula. So we need to find out what is our log A base B. What is our log A base B? Log 16 base 4. What do we get here? What do we get? We get 2. So so we can see that looking at the definition, we can see that this function log A base B is bigger than our Fn. Sorry, it's bigger than K. It's bigger than our K, which is 2 is bigger than 1. Okay, so therefore, what is the answer for this one? So if you look at case 1, it would be theta n log A base B, which is n log A base B n to the power of n squared. So therefore, the Tn is equals to order of n squared. Are you good? You don't have to do anything. You just put in the value. You don't have to do any calculation. So for the second one, what is the value of A? A is 3. B is
2.
2. F of n is n. K is 1. P is 0. Log 3, 2. And we want to compare with 1. So is it bigger or smaller? It's bigger, right? So therefore, we can say that it's case 1. Therefore, the running time complexity would be theta n to the power of log 3, 2. I don't know what is log 3, 2. So this would be the running time complexity for this one, for B. Okay, so this would be running time complexity for B. Are you good so far? You can use calculator to find out what is log 3 base 2. Okay? And you know it will definitely be bigger than 1. Okay. Alright, so let's look at the next example. Example for case 2. Do you want to try this? So our A is equals to 4. Our B is equals to 2. Fn is n squared. Our K is 2. Our K is 2. Our P is 0. Okay, so log A base B is equals to log 4 base 2, which equals to 2. Okay, and then our K is 2, so therefore we can say that it is case 2. But then case 2 have 3 conditions. Now we need to look at the P value. So our P value is 0. So is it A, B or C? A, B or C? If it is 0, it will be
A.
A, right? So let's plug in A. So we're going to get the running time complexity would be, so A theta of n to the power of K. What is K? N squared log P is 0 plus 1 is 1. N squared log n. That would be running time complexity for that recursive function, recursive algorithm. Okay, so that would be for the first one. Okay, for B. For B, so B, what is our A? A is 2. B is also 2. Our f of n is n log n. Our K is, what is our K? Our K is
1.
our P.
1.
Okay, so we know that this is case 2, but then for the P, is it A, B or C? So P is equals to 1. So if P is equals to 1, we apply the same one, A, right? So the answer would be, the n would be theta of n to the power of K log 1 plus 1 to n, right? So we just plug in the value. Okay, so this would be the running time complexity for that recursive function. Okay, so you can continue and do for the rest of the question, and I think I have given you the answer as well. So maybe you can try in your own time. And we have other examples as well. Same goes for KC. Okay, so KC, let's just do one for case example for KC. Example for case C, since it's already have a solution here. Okay, same thing. Okay, you find what is the value of the A, B, F, N, K, and P, and then you just apply the formula. Okay. All right. The only thing about master method is that not all recursive relation that you can use the master method. Okay, so there's a condition in order for you to use that. Okay. All right. But before that, let's look at this example. Why do you think that this you cannot use this master theorem to solve this?
Because A is less than or equal to 1.
How would you solve this problem? In fact, even without the master theorem, you cannot break into the work into half, can you?
Yeah.
N over 2. Maybe you can. I don't know how is the 3 is going to look like. 0.5. How do you break it into half? Can lah, it will be like crazy. You need to trace it like you need to break it into half. Can? No, I don't think so. I don't know how would the 3 look like. Okay, that's why something like this you cannot use the master method to solve. Okay, and these are some other condition that you cannot use master theorem. Okay, so the first one here. Okay, because your A, so this is your A, it's not a constant. Okay, and then the number because the number of sub problem needs to be fixed, because else your 3 is not going to break equally. Okay, and then for this one you need to make sure that okay, and then this one, the polynomial difference between f(n) is n log a base b. See below. Oh yeah. So in the second trimester, the difference between can be expressed ratio. So okay, so this one is actually related to the common method. Okay. Okay, so the one that I use in this class is the how do you call that? The simplest master method way for simplest master method way. Okay, so there are other ways that you can apply the master method. Sometimes you may find that they are comparing between B and A and B to the power of K or something like that. So the comparison will be different, but then whatever it is, the condition will be the same. Okay, so for common as well, the way they write the definition is a bit different, but the master method is the same. It's just that this is the simplest, easiest way that all you have to do is just identify what are the value for all those variables, and then you just plug it in into the master method. Okay, so if you want to know further about this one, you can read the common book. All right, and we have seen this one just now. We cannot have a less than 1. And then this one, so basically this one, the fn, it's not positive. Okay, we want to make sure that our is asymptotically positive. And then okay, so we have a regularity violation. Okay, so you cannot apply master method for this one as well. Okay. All right, so you can actually do this as well. So we have seen this one is equals to n log n. You can try to apply the back substitution method as well as the master theorem to see whether you can get the same answer back. Okay. You have to supposedly you need to have to get the same answer. If you get the wrong answer, that if you don't get the same answer, then there must be something wrong with in your substitution method or the master theorem. Okay. All right. Okay. So any question? So next week we're going to be looking at sorting algorithm. you're going to be surprised to see that some of you can actually do sorting in linear time. I really like the algorithm, so I cannot wait to show it to you. So yeah. So do you have any question regarding today's lecture? If no question, then we'll end the class for today, and I'll see you during tutorial. Is that all right? Okay. My working, you mean the thing yang I conteng ni? Can you actually read my handwriting? Okay. All right. So I will just put it inside the drive. So I'll put like a folder annotated. So I'm just going to put in my slides, the one that I have already like draw all over the place for you. Okay. So I will see you in the tutorial on Thursday. Okay. Please don't forget to sign your attendance. Yeah. Okay. I have another.
I
Yes.
have a question about the tutorial.
Yes.
I am in tutorial group 4, so I am supposed to
Go
be
to
attending.
Dr.
Yeah, but the time of the tutorial is Thursday from 9 to 11, right?
Mm.
I want to be in that time slot because other than that I have other lectures.
I think Dr. Raja is have two slot. One is the one in the morning, and the other one is in the afternoon, if I'm not mistaken. Or is it that hers is what? Because my morning slot, mine is already maxed out. For I have 34, 35 in the morning. I have yeah, but for Dr. Raja, I think you still have because her class is empty. That's why she make an announcement just now.
Okay, thank you.
All right. Okay. All right. So in that case, I will end the class for today. I have another 2 hours lecture after this, so hopefully I can go through until 7. Okay. All right. So I'll see you on Thursday. Thank you, everyone.
Thank you so much, Doctor.
Thank you, Doctor.
Thank you, Doctor.
Bye.
Thank you,
Bye.
Doctor.
Bye.
Thank you, Doctor.
Thank you, Doctor. Thank you, Doctor.